Hi guys and welcome to a brand new video from Maths Guru. My name's Darren, welcome to see you. Thank you very much for dropping by. What are we going to do today? Well, it is a brand new section of the Further Maths course. And if you don't know what Further Maths is, really don't worry about it because you're going to by the end of this. If you're doing networks and all that type of stuff, then this video is going to explain a lot of the language we're going to use. So in fact, the first 3 or 4 videos is going to be making sure you've got what you need to know to be able to smash through the rest of the stuff. The last 3 or 4 sections of this particular module get a little bit funky, but if you understand all of the stuff I'm about to do, you should be fine. If you haven't already done so, subscribe and like and let your mates know. That would be greatly, greatly appreciated. Now, there is no recap of past learning because, as I say, this is sort of new stuff, okay? You may have done this in year 11. You may have done it in previous parts of school. If you have, awesome. Then let's just get started and look at what a graph is. Well, basically, what do we say here? Well, we live in a connected world. Pretty much if you're on TikTok or, Facebook. I know, Facebook's so yesterday for you guys, I get it. Instagram or whatever else, you're connected. You're connected in a network. You're connected to people. And every time you look at a video, you're effectively connecting with them. For maths, we don't get that too complicated because, it's billions of people. What we're going to do is look at this type of thing here, which is called a graph. Yeah, it looks nothing like the graph that you did before, is it? Remember, graphs you did before had little bar charts, and we're all very happy with bar charts, but not now. We're going to start looking at things like this. And a graph shows connections. Pretty much that's it. Now, Barry tries to confuse the flipping life out of us, and he's going to use different language to all mean the same stuff. And remember, that's where maths tricks you. Nothing more, nothing less. It's just the stupid language. Now, in Australia, you're allowed to use summary books. If you're here in Victoria, I would make sure your summary book has all the random language, and particularly when we get onto Eulerian paths and circuits and all that type of stuff, your summary book is going to be vital. All right, so let's call this a graph. It's a connection showing sort of Anna, Brett, Francis, Ethan, Cora, and Dario. Great names. Yeah, and obviously every time there's a connection between them, every time there's some sort of link, maybe they can communicate with each other, maybe there's a road to their house, maybe there's, I don't know, a secret message sort of network. Likewise, it can all be shown in this particular way. Now, as I say, the language gets really, really important. So we must make sure that we use the right language. And here we go. A connection between two people, all right, is called an edge. So this line here between Anna and Francis is an edge. This line here is an edge. That line there. So all of those blue lines, which I've now done red over, are all edges. The places, the people, are called vertices or a vertex, yes? So Ethan is a vertex, and Dario is a vertex, and Francis is a vertex, and so if we start using that language, we're going to smash it. The next thing we need to know, and again, this all comes in later on for paths and circuits and Hamilton stuff, so this is going to build up into a video 3 or 4 from now, but again, it's important you understand that a degree of a vertex is how many connections are coming in to a particular vertex. So for example, if we look at Anna here, as I've said, what do we notice? We have 1 line coming in, 2 lines coming in, 3 lines coming in. So there are 3 connections coming into Anna. So we would then say that the degree of that vertex is 3. And how would we write that? Well, we could write the degree of Anna is equal to 3. Yes, so the degree of Anna is 3. What about Francis? We've got 1, 2, and 3. So again, that is degree 3. Ethan, on the other hand, only has 2 connections coming into him, so in which case that would be a degree 2. And knowing the degrees of these things, again, comes in handy later, particularly when we're trying to wander around these particular connection diagrams. Now, loops, yep, basically Ethan, very much like me, is going a little bit loopy. Pun intended. Why? Because he effectively can talk to himself. Now, if we were talking about, or if this was about talking to people, then the fact that Ethan basically connects round to himself, yeah, that means he talks to himself. And it's a loop. Yes, now obviously we may have road networks that loop around to themselves. I can't think of a practical example of why that would be, but anyway, we might have that situation there. One of the things that's really, really important to note here is that actually, if I was going to look at the degree of Ethan, what do we notice? Well, that loop, if we were to ignore it, actually has 2 connections. Yes, the loop leaves and it comes back in. So if we were going to look at the degree of Ethan, we would actually say that Ethan would have degree 4. That's going to come up a little bit later, right? But again, we can only see one loop in there. Now, we, generally speaking, use things to go road networks. That's, I think, further maths in many cases uses the idea of road networks. And so we're going to look at what a simple graph is. And again, this is language. A simple graph doesn't have any loops. So this is the important thing here. The simple graph has no loops. Can we see any loops in there? No. Although it looks like there's a big loop going around between A, C, D, and B, a loop would quite literally be around and back to itself. So what I'm going to do is get rid of that loop, if we would be so kind, and then that is a simple graph. An isolated vertex is very much like me at a nightclub. Yes, I go to a nightclub and I'm very isolated. If you ever see me at a nightclub, I'm a bit old for nightclubs now, to be perfectly honest with you, and I'm fairly sure that Revolver wouldn't let me in. They don't have a granddad's discount, and I'm certainly not paying $20 or $30 to get into a nightclub. It's just too much. But the point of it is, there, point E is out on its own. It is isolated. So when we have a point on its own, it's an isolated, and don't forget, vertex. Degenerate graphs. It fascinates me where they get this language from. Degenerate, that's a horrible word in any other context, but let's throw it into a further maths course. A degenerate graph is basically where, what does it say? All the vertices are isolated. There's no connections between any of them whatsoever, all right? And again, that would be me and my friends at a nightclub. I have no friends. I don't know who A, B, C, and D are. Anyway, moving on. Connected graphs and bridges. All right, so connected graphs, we know a connected graph is where one or every vertex is connected, all right? So that's our connected graph. All of the vertices are connected together. Yeah, we don't see any isolated vertices, no loners. Now, what we need to realize is that between D and E is something called a bridge. So, and again, if you look at this, it might well be that if we had, in a real context, a river going between those, that's a bridge over the river. Coming up a bit later on. Yes, so we've got the whole connected thing with a bridge between that. D and E is a bridge. Again, do you notice how this is all language? Yes, I know. A complete graph. All right, so we've got the connected graph, all of them connected. A complete graph is where every vertex of a graph connects to every other vertex. All right, so in this situation here, what do we notice if we look at point D? It's connected to C, it's connected to B, and it's connected to A. They are the only vertices in the diagram, and if we look at all the other vertices, they are all connected together. So that's a complete graph. All right, again, very, very important you understand the language here. A subgraph is basically very much that, like it's a little bit, it's a small part of the graph. Now again, it doesn't have to be drawn in exactly the same way. If we look at this here and call that our master graph, yes, then what we can see is that our graphs here and here are basically subgraphs. They are just small parts of the diagram that are, well, they can look exactly the same, or they could look very, very different. So if we notice here, we've got in this sort of, let's call that A, we've got A, B, and F connected together, which is just this part of the graph here. Subgraph, literally they've just drawn that little part as a subgraph. What do we notice about part B? Let's call that part B. Well, again, we've got connections from A to B, B to C, C to D, D to E, and E to F. Now, all of those connections exist in this diagram here. Yeah, I've not made up extra lines, I've not missed lines out, there are connections. If I was to add another line here, for example, well, that would no longer be a subgraph because that line doesn't exist in my original diagram. Just rub some of these out to make sure that we don't confuse. And remember, all of these notes are downloadable on mathsguru.com. Yeah, so if you go over to mathsguru.com, totally free to sign up. Downloadable notes, time codes, all sorts of stuff over there, and so much more coming. About to, at the end of the day, record a load of questions from VCAR exams. Hopefully they'll upload as well. Isomorphic, again, isomorphic. That's a summary book word, isn't it? Yes, or equivalent graphs. Now, long story short, an isomorphic graph is exactly the same diagram drawn in a different way. I know. Why would you? Well, we're going to come up to that in a moment. All right, so an isomorphic graph is a graph that is drawn in a completely different way. And if we look here, and we'll call those graphs 1, 2, and 3, they are absolutely identical. They have exactly the same number of vertices, And the edges connecting each vertex are also identical. Again, you can't change the graph, all right? There can't just be a random connection. So do we notice, there's no connection between point B and C there, so I can't suddenly make a connection between point B and C on my other graphs. But again, if we check, there's my connection between A and B, there's my connection between A and B, there's a connection there between A and D, there's a connection between B and D, A and C and E. And again, totally, absolutely, I've got no more vertices, no extra edges, it is the same diagram. And number 3 looks exactly the same. Planar graphs, and I'm getting to some examples in a moment, all right? Trust me, once you've got the language, you're gonna smash through this. Planar graphs, all right? Now, what are planar graphs? They are graphs that can be drawn in exactly the same way where the edges don't cross. We don't like crossed edges. Why? Well, we might get confused there and think, well, that's actually a vertex. It isn't, all right? There is no thing there. Also, by redrawing these, we can use something called Euler's rule. Ooh, who's Euler? Now, a lot of people go, Euler? It's not Euler, it's Euler. Anyway, all right, so planar graphs are graphs that can be drawn the same way. And the way I think of this is if you look at what have they done, they've taken this line here, A to D, and you can think of it as like a elastic band. So, or rubber band in Australia, where basically you just grab it, you stretch it over. Now, obviously, if this were a road network, that'd be like just not going to work. I mean, how's that going to work? You just grab a road and drag it, not going to work. But the idea here is we still have exactly the same connections. We've just drawn A to D on the outside. We've dragged it over point E so that none of my edges are crossing, right? So that's a planar graph. No edges are allowed to cross. Now, why is that important to us? Well, we have this funky thing called Euler's rule. All right, now basically, he came up with an idea that if you had vertices plus faces minus edges, and that equals 2, then the diagram is planar. Now again, we'll go back to this, all right? A diagram can only be planar if it follows Euler's rule. Now again, the way I remember this formula is very fat elephants, and I put a plus there and a minus there. There is probably better ways to remember this. If there is, leave a comment below. And guys, if you are watching this, do me a favor. I'm sitting in here talking to myself. It's random. I know I'm talking to you, but I'm actually sitting in a room talking to myself. If you can leave me a comment and just let me know whether this video is useful, what I can do better, what I can do worse, that's random, I'd be really, really grateful. And tell your mates about these videos as well. Shout outs on TikTok and YouTube and whatever else are really greatly appreciated. No one watch Maffs videos. And everyone says, oh, you deserve more subscribers. Well, I can't get more subscribers unless you pitch in. Thank you very much. Right, so what is this all about? So V we already met is vertices. E we've already met is an edge. What on earth is a face? And basically a face is a section of the diagram that you can effectively color in. So it's like an enclosed section of the diagram between vertices. And if we look here and we've got A, B, C, D, E, F, we notice that we've got a colored in section here, that's face 1. This is face 2 and face 3. So that's all the inside sections. We also have to count the outside of the diagram as well. So all of the outside to infinity and beyond is also a face, right? And that's why they call this F4 for face 4. Again, let me just erase some of this so that it makes sense. And so, why are we going to use all this stuff? Well, here's some examples, and thank you very much, Cambridge, for allowing me to use your further maths examples. You guys rock, and if you aren't using the further maths textbook out there, it's phenomenal. So many questions, and their chapter review sections are phenomenal. Now, you'd think they were sponsoring me for this. Anyway, right, here we go. A connected graph is shown. How do we know it's connected? Well, if you remember, all the points are joined together. Ka-ching, thank you very much. What is the degree of vertex C? Right, so let's look at vertex C. There it is. A degree is how many points are coming in. 1, 2, 3, 4. And there we go. We know that the answer to the first part is 4. Which vertices have a loop? Again, and we're going loopy. Loopy. Here we go, loopy-loo. There is a loop. And there, weirdly, is a loop. There are only 2 loops. And so we would say for that second part, let's write the answers down here. Let's do the first dot point was 4. The second dot point would be B and F, if I remember rightly. What is the degree of vertex F? Now, remember, this is the trick. If we look at that F how many lines are coming into the dot. Ignore the loop, just count how many lines are coming in. 1, 2, 3, 4, 5, and so the degree of f is 5. And a lot of people get tricked there. They go, oh, but it's a loop, it's only 1. No, it's not, because remember, a loop, if I drew that loop at f, we've got one line here and one section here coming into that dot or out of the dot. A bridge exists between two vertices. We've got this. Can you see the bridge? All right, now I know my scribbles are a little bit all over the place, but it's between A and C. Draw a subgraph of this graph. Now there are lots of different subgraphs. And again, if you remember, a subgraph is just a section of the graph. I could quite literally do so it had to involve A, B, and C. A, B, and C. So let's do that. There's my connection between A and B. There is my loop. And let's just draw that line there. A, B, and C. And ladies and gentlemen, that is a subgraph. There are so many other examples. Show that this graph is planar by redrawing it such that no edges cross. So obviously there isn't a vertex there, so we've got to try and do something with that diagram. What can I do? Well, I'm going to think of the connection between C and E like a rubber band. So I'm going to do B, C, D, E, F, and A. Let's connect those together because we've got the outsides connected together. Let's do the letters A, B, C, D, E, and F. Okie dokie. And so we now want a connection between A and D because we're going to keep that one and we're going to drag that rubber band from C and E so that it does this. And no one says anywhere that these have to be straight lines, by the way. I know they're always normally drawn in a straight line, but you can drag that over and make it curved. Job done. And I have no idea just what that was all about. For the graph shown on the right, we'll redraw the graph in planar form. Okay, again, we're going to redraw the graph. So we've got E, A, B, C, and D. So let's write E, B, nearly wrote those wrong way around, A, C, and D. We're going to connect E and A together, and all of those outsides are connected together. I'm going to keep B to D, and I'm going to drag that connection from A to C over there. Ka-ching! Thank you very much. Now, remember, if it's planar, which that seems to be, we should be able to verify it using Euler's law. So let's see. So we know that very plus fat minus elephants must equal 2. For that to be true, right, so let's have a see. We got vertices, 1, 2, 3, 4, 5. So there are 5 vertices. Those are the letters on the edges, remember. Plus the number of faces, and leave that for a moment, minus the number of edges. Now again, edges, so we've got 1, 2, 3, 4, 5, 6, and 7. Right, so there are 7 edges. I'll do that, not in highlighter. Now, whatever happens is that's got to equal 2. Now again, this part here is where we do the faces. Okay, so what are the faces? Those are those enclosed sections. So we've got one here, so there's F1, F2, F3, and all the way outside. So F4, so there's 4 faces. So does that actually make 2? 5 plus 4 is 9, minus 7 does equal 2, smiley face. So in which case, using Euler's rule, we know that that is actually planar. Now, obviously, they don't always give you diagrams. Sometimes you have to work out missing things using Euler's. What am I saying? I don't know. A connected planar graph has 6 vertices and 9 edges. How many faces does the graph have? Now, because it's connected and planar, yeah, so planar means we can use the formula. So V plus very fat elephants, that must equal 2 for it to be planar. Okay, so we know that we got V is 6, we've got E is 9, plus F equals 2. Now again, you can do this in all sorts of different ways. You can solve on your calculator, or we can do it. So 6 minus 9 is minus 3. And I'm going to add 3 to both sides, which gives me 5. So this thing would have to have 5 faces if it is planar. All right, so let me see. Oh, it says draw a connected planar diagram with 6 vertices and 9 edges. Okie dokie. 1, 2, 3, 4, 5, and 6. And you're going to say, why did you draw it that way? Basically, I know the answer. Again, there is not one diagram here. There can be lots and lots of different diagrams. So we got, what did we have? We had the 6 vertices. We want to make sure that we get 9 edges. 1, 2, 3, 4, 5, 6, 7, 8, and 9. Oh, I've drawn a fan. How exciting. So let's call that A, B, C, D, E, and F. And now we're going to do is just make sure that do we have 5 faces? Well, here is face 1, face 2, face 3, and face 4. Those are all of those enclosed sections inside. And if we remember, we've got to have one outside. And ka-ching, ladies and gentlemen, as I say, I knew the correct answer. So there we go. All right, but as I say, there are other examples that may exist. And ladies and gentlemen, that is the end of this video. Thank you very much for watching. Lots more coming. Other videos are a little bit shorter, but again, there's a language here that was important. Hopefully you've enjoyed it. As I say, do me a favor, give me a shout out on TikTok or YouTube or Instagram or wherever, because as I say, people will keep saying, oh, you deserve more subscribers, and I would love more and more subscribers, yeah? I'm doing this for fun and to help you guys, and if you can do something to help me back, greatly appreciated. If not, I will see you in another video. You take care and stay safe. See you again. Thanks very much for watching, guys. Yes, this is the end of another video. If you haven't already done so, can you click on my subscribe button? Yes, it doesn't mean anything other than the fact that I know that you are watching. Yes, it's greatly appreciated. Otherwise, I feel like I'm sitting here just talking to myself. And then, yes, there is mathsguru.com, of which you can see a still of now. And what is over there? Well, all the videos ordered by textbook, ordered by topic. You can search for the videos. You can download notes, time codes, exam questions, and so much more coming up. Yeah, it's absolutely free to join. So I'm done. Thank you very much. I hope to see you in another video. Give me a shout out to your mates if you can. I just want to make sure that everyone finds maths interesting and easy. All right, take care, guys. See you again. Bye-bye. Stay safe.